Now, this triangle is useful, but you can imagine that if I ask you to write down a plus b to the power 27, then you don't want to have to write down 27 layers of this triangle just to find the answer. So we're going to need a shorthand to quickly talk about arbitrary exponents, and that's what the binomial theorem is going to give us. So we need one more piece of notation before we talk about the binomial theorem, and that is we have to talk about the binomial coefficients. So for that, we first introduce the concept of a number factorial. So this is maybe a new concept, and this is denoted as n exclamation mark, where this n right here is a natural number. And what we mean by n factorial, n exclamation mark, is n times n minus 1 times n minus 2, and you go down one step at a time, times 3 times 2 times 1. So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120. And there's one special case to be dealt with separately, 0 factorial, that also often comes up, that is 1 by definition. And so now we can introduce the binomial coefficients. So they will depend on two parameters, n and k, both of which are natural numbers. And they're denoted as follows, so parentheses n, k, like this, you note the two numbers one above the other, and this is n factorial divided by k factorial n minus k factorial. So for instance, if we want to compute the binomial coefficient 6, 3, that's 6 factorial divided by 3 factorial, and then 6 minus 3 factorial. This here is 3, so another 3 factorial, and we get 6 times 5 times 4 times 3 times 2 times 1, divided by 3 times 2 times 1, 3 times 2 times 1. Now you see a nice cancellation, 3, 3, 2, 2, and 1, 1, even though that doesn't really matter. And we're left with 6 times 5 times 4 divided by 6, so that gives us 20 for that particular factorial. And so why are these coefficients important? Not only are they going to give us some way of writing down the binomial theorem, but they also occur in, for instance, probability theory. In combinatorics, and in a wide variety of applied fields. So especially probability theory, if you take the probability and statistics course in Bachelor 3, you will see these coefficients come back a number of times. And so why are they so ubiquitous? Well, they actually have a standalone meaning, and they represent, so this coefficient represents the number of ways of choosing k objects from n. So out of n, choosing k, how many ways are there to do that? And just to see this in action, and this is maybe also a bit difficult to write down, but I'll try my best. So let's say we want to choose 3 out of 5, and here we'll denote the 5 by A, B, C, D, E. So how many groups of 3 can you make from 5 objects? Well, there's A, B, C, there's A, B, D, there's A, B, E, there's A, C, D, there's A, C, E, and then there's A, D, E. Now I have to make sure that I don't forget any. So now B, C, D, B, C, E, B, D, E, and C, D, E. So I think I didn't make any mistakes. So we have 10 such groups of 3. And now let's use our new definition. So number of ways of choosing k from n. So we want to choose out of 5, 3 things. So that's binomial coefficient 5, 3, 5 factorial, 3 factorial, 2 factorial, and that's 5 times 4 times 3 times 2, 3 times 2 times 2. And now I simplify 3, 2, 3, 2. And that gives me 20 divided by 2, which is 10. And that agrees exactly with the answer that we found earlier. Notation-wise, this quantity is sometimes also denoted as capital C, K, N. And when you see this expression, then it's usually referred to as combinations. It's called combinations of k elements out of n. And in the predominantly American literature, this coefficient, this binomial coefficient, is also sometimes written as n choose k. And I like that because it's short and it tells you exactly what the binomial coefficient does. Out of n, choose k. So now that we have the binomial coefficients, we can rewrite Pascal's triangle, and we're going to do that by revisiting the triangle first and then seeing what patterns we can develop. So we had 1, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1, and so on. And so now the binomial coefficients appear as follows. So that first one at the top, we can write it as 0, 0, because 0, 0 is 0 factorial, 0 factorial, 0 factorial, so that's 1 over 1, which is 1, so okay, that matches. And then likewise for the next set of ones, so that this we can write as 1, 0, and 1, 1. And in fact, if you have k for the binomial coefficient, that is going to be k factorial divided by k factorial, k minus k factorial, so that's k factorial over k factorial, and that gives us 1. So, and one other property that I'll prove, and then we'll move on with the triangle. So k0 likewise is k factorial, 0 factorial, k minus 0 factorial, so that is also 1. So that tells us that 1, 0, binomial coefficient, that's 1, 1, 1 is also 1. And now we can move on, so we can write the next layer as 2, 0, and then something here that I'll fill in, and 2, 2 here, using this property, and this property for the first one. And now if you look at this, you can probably guess what we have to put in here, so it's probably going to be 2 and then 1. And let's check that. So 2, 1, what is that? 2 factorial, 1 factorial, 1 factorial, and that is indeed 2. Then moving on to the next layer, we get 3, 0, and probably think this is going to be 3, 1, but let's check it. And actually, let me write this in a color so it stands out. 3, 1, 3, 2, and then 3, 3. And so what do we know about 3, 1? Well, that's 3 factorial, 1 factorial, 2 factorial. So that's 3 times 2 divided by 2. That is indeed 3. And 3 times 2, you can verify for yourself, it's also 3. Great, moving on. 4, 0. And then 4, 1. 4, 2. 4, 3. And 4, 4. So we can maybe validate one more coefficient just to see that it works out, and then I hope the pattern makes itself clear. So 4, 2, for instance, that's 4 factorial. Actually, I want to make some space. 4, 2 is 4 factorial divided by 2 factorial divided by another 2 factorial, so 4 times 3 times 2 divided by 2 times 2, so that's 3 times 2, or 6, and that indeed gives us that 6. So in general, you can continue with this, but in general the end layer of the triangle is going to have binomial coefficients n0, n1, and so on, up until n minus 1, n. And now this gives us a particularly nice way of writing the expansion of a sum of two things, and that is what the binomial theorem is going to give us. So let's revisit the thing that we started from, a plus b to the power n. The binomial theorem tells us that we can write that as n choose 0, a to the power n, b to the power 0, n1, a to the n minus 1, b to the power 1, n2, a to the n minus 2, b squared. And you keep doing that, so in each case the salient features are, we have a binomial coefficient where the lower number goes up by 1, and then we have, so this changes into this, and so on. And then we have an exponent for a that starts with n and then lowers by 1, n minus 1, n minus 2. And we have an exponent for b that goes up, so 0, 1, 2. And that pattern continues until n minus 1, a to the power 1, b to the power n minus 1, and n, a to the power 0, b to the power n. And of course you already know that n0, anytime there's a 0 in the binomial coefficient, that's just 1. Likewise nn, that's always 1, no matter what the n is. And then there's two more things that are worth calculating by yourself. N choose 1, that's going to be n, no matter what the n is. And n minus 1, choose n minus 1, that's also n, no matter what n is. So for instance, n1, that's n factorial 1 factorial n minus 1 factorial. Now you can see that's n minus 1, and multiply by a whole bunch of other numbers, n minus 1, n minus 2, and so on. And of course the n minus 1 cancels, as do all the lower order terms, and we're left with just n. So this formula by itself can be written very compactly by using the summation notation. So capital sigma k going from 0 up until n, binomial coefficient n k. So that's the thing that changes here. And then a to the power n minus k. So that's our exponent for a. B to the power k. So that's also what we saw there. And in this way, we can write down the formula very concisely. So let's do one short example of this. So let's compute square root of x minus 1 to the power 7. So that's going to be sum k equal to 0 till 7. 7 choose k, square root of x to the power 7 minus k times minus 1 to the power k. And now we can write this out. And now we can simplify the expressions. We can use what we know about the binomial coefficients to actually calculate what these values are. So we know 7, 0, that's 1. 7, 7, that's also 1. And now we just fill in. We can either calculate directly or we can go look back at the Pascal triangle. So that still works. And that gives us 7 here. And then 21 here. 35, 21, 7, and then 1, as I mentioned before. And now, of course, you can write out what minus 1 to a certain power is, and you can simplify these powers right here. So, for instance, square root of x to the power 7, that's x to the power 7 over 2. So, remember, square root of x, that's x to the power 1/2. So square root x to some power k, that's x to the power k divided by 2. And so here we get 7/2. Here we get x to the power 3, x to the power 5 over 2, x squared, 3/2, 1, 1/2, and then the sign, that's very easy. So this is plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, and minus 1. And then collecting all of the simplifications, we get x 7/2 minus 7 x to the power 3 plus 21 x to the 5/2 minus 35 x squared plus 35 x to the power 3/2, 21x, 7 times square root of x plus minus. Okay, so it's a lot of writing, but ultimately it's the formula that dictates what has to go where. And so the binomial formula you will see appearing a lot of times when you want to precisely expand something like this. And then the thing to keep in mind is you can write this out, this exponent as a sum of terms, and you have the binomial coefficients in there. Sometimes you won't even have to calculate the binomial coefficients. You can just say, oh, they're numbers that I drag along. And sometimes you have to calculate the coefficients. So then you can either use the definition, or if n is not too large, say 5 or less, you can quickly write down Pascal's triangle and see from there what the answer is. So we're not going to cover the proof of the binomial theorem in detail, but what I would like to do is point out a very nice geometric proof. It's not really a very formal proof, but it gives you some intuition as to what's going on. And it also points that sometimes geometry can say something about something that looks really algebraically. So in this geometric proof, let's look first of all at the case where n is equal to 1. So we do a plus b to the power of 1. And graphically, we can represent it as taking a line segment of length a, and then adding to that a line segment with length b. And so that length, that is, well, that's a plus b. So no surprise there, a plus b to the power 1 is a plus b. It gets a little bit more interesting when you look at the square case. So here we're going to look at a square on the left-hand side, and this square has sides a plus b. So the red square inside here has length a for the sides, and the green rectangle has the lower side is b long. So this whole quadrangle is a plus b squared in surface area. And now, as the picture suggests, we can pull apart this quadrangle into 4 other quadrangles. We have one here that's a squared in area. So here we're going to look at areas. And then we have 2 green rectangles. So remember that they have lengths a and b. So the total surface area is a times b times 2, because we have 2 of them. And then we have a little blue part here in the corner, and that's b squared in area. And so the whole area, a plus b squared, therefore is a squared plus 2ab plus b squared. Now if we move to the exponent 3, then instead of areas, we're going to talk about volumes. And here we do the same thing. We make a cube, and the side of the cube is a, so this is also a. And now we have to be a bit careful. So the green thing right here still has length b, b, b. So all the small sides are b. Now we can pull apart this big cube, whose volume is a plus b cubed. And we can say, well, the volume of the big cube is the volume of the red cube, that's a to the power 3. And then we have 3 light green areas. There's one at the back that you can't see. So we get 3 times the volume of this light cube, and given that this has sides b and then a, the volume of one such thing is a squared b. So 3 of those gives us 3 times a squared b. And then we have the cyan colored rectangles here. There's again 3 of those, and now they have sides b, b, a. So the area, the volume of one is a times b squared. We have 3 of those, so that's 3 times ab squared. And then last but not least, we have that little blue cube that has side b, so the total volume is b cubed. And we see that a plus b cubed, the volume of the big cube, is a cubed plus 3ab squared, 3a squared b plus 3ab squared plus b cubed, b to the power 3. You can keep doing this in 4 dimensions, but I don't know about you, but I have a hard time thinking in 4 dimensions or in higher dimensions. And so there it breaks down a little bit. But if you think about it carefully, you can sort of expand this to higher dimensions. This is not a formal proof, but we don't need to prove here, and therefore we will skip it for this.